are the operations on matrices. So these are inspired by operations among vectors. We can add vectors and we can take scalar multiple of a vector. So we can do the same thing with matrices. So suppose we have three matrices A, B, C of same size, and there are scalars alpha and beta. So I will, when I talk about matrices, I will assume in the background that these are real matrices. When the context is different, I will say these are complex matrices or rational matrices. But when we talk about real matrices, we will use real numbers as scalars. Okay, when I say scalar, it means they are real numbers if we are dealing with real matrices. So A plus B is equal to B plus A. You can easily check that this is true. So addition of matrices is commutative operation. It is an associative operation. You add, may take three matrices, you add A and B, and then add C, that the answer is same as adding A, and then adding to it the sum of B and C. And if you write down the proof of this, you will see that this is really derived from the corresponding statement for real numbers. Addition of real numbers is commutative. Addition of real numbers is associative. And these two rules then translate into the corresponding properties of addition of matrices. That addition is commutative, and addition is also is associative operation. So if we don't use brackets, it doesn't cause any confusion. So when I say I have finitely many matrices A1, A2, AN of the same size, then when I say add the matrices, it is a unique matrix. It is understood what it is, because we can rearrange the manner in which we add these matrices, and because of associativity, it doesn't matter how you add them, how you bunch those matrices to add and arrive at the answer. Okay. Scalar multiple of matrices satisfies this property that it is distributive over addition. Alpha times A plus B is alpha A plus alpha B. Okay. And again, this is very clear from the definitions. We are adding component wise, and we are, when we take scalar multiple of a matrix, we are multiplying every entry by the same scalar. So alpha times A plus B is alpha A plus alpha B. Similarly, matrix multiplication and scalars, they satisfy this fourth property that alpha plus beta times A is same as alpha A plus beta A. Okay. And alpha times beta A is same as alpha beta times A, and therefore we can write it as alpha beta A. So take minus 1 times A, that is a scalar multiple of A. We will write this as minus A, so that we don't have to type or write the minus 1 in round brackets. And similarly, A plus minus B, we will write A minus B, and we understand that this is the sum of two matrices, A and minus B. Transpose of A matrix, this is a very important operation. We take M by N matrix, where the general entry is AJK. Its transpose of this N by N matrix is a N by M matrix, and we write it as A transpose, transpose as a superscript, and the general entry is AKJ. Okay, so if I have a M by N matrix, there are M rows and N columns, but its transpose will have N rows and M columns, and the first row of A becomes the first column of A transpose. Second row of A becomes the second column of the A transpose. Similarly, first column of A becomes the first row of A transpose. Second column of A becomes the second row of the A transpose, and so on. So that's the relation between A and A transpose. Row vectors of A becomes column vectors of A transpose, right? And we can check that double transpose of A is same as A. Transpose of A plus B is A transpose plus B transpose, and alpha A transpose is alpha times A transpose. So this is how transpose operation behaves with respect to scalar multiplication and addition of matrices. So be careful. Double transpose of A, you get back A. It is clear from definition. And now we can rewrite our definition of symmetric matrix in terms of transpose. A matrix is symmetric if and only if A transpose is A. Okay. A matrix is skew symmetric if A transpose is minus A. Transpose of a row vector is a column vector. Transpose of a column vector is a row vector. Okay, so this is how transpose behaves with respect to addition and scalar multiplication of matrices. Okay, are there any questions? People can ask questions in chat box.
I don't see anything as of in the chat.
Okay, all right. Yeah. Okay. Now we define linear combinations of row and column vectors. Throughout the semester, we will be dealing with linear combinations to do various things in linear algebra. So let us define what is the meaning of linear combination of row and column vectors. So fix M and N and take M scalars, alpha 1, alpha 2, alpha M. So these are real numbers. And take vectors in R1 cross N. That means these are row vectors with same number of components. There are N components in every one of these vectors, A1, A2, AM. Then we can take their linear combination, alpha 1, A1 plus alpha M, AM. This is, so we are adding vectors component wise, and we are taking scalar multiple of these row vectors component wise and then adding them. So this is a linear combination, and it is again a row vector of the same size. That is, it has n components. So vectors with n components, row vectors with n components, we can first scale them by arbitrary scalars and then add them. Then this is called a linear combination of these vectors. Similarly, if we have B1, B2, Bm as column vectors with n components, so all these column vectors should have same number of components, and suppose these are n components and they are all real column vectors, we can take their linear combination alpha 1 b1 alpha m bm, and from the definition it is clear that this is again a column vector with n components. So this is called a linear combination of these column vectors. Now we have very, very special column vectors called EK. These are column vectors where only one entry is 1, namely the kth entry is 1 and other entries are 0. So these are column vectors. EK denotes a column vector where only kth entry is 1, other entries are 0. And if we have an arbitrary column vector, so now you see I have changed. I'm not writing column vector as a column, but as a transpose of a row vector. Yeah? So B is a column vector with components B1, B2, Bn, but I'm writing as a transpose of a row vector simply to save space. Okay. So if I have this column vector with components B1, B2, Bn, you can check very easily that it is a linear combination of these n column vectors E1, E2, En with scalars as the entries of the column vector. So B is equal to B1 E1 plus BK EK plus Bn En. So this is a linear combination. That means if I take vectors in n-dimensional space Rn, then all the vectors in Rn can be generated by addition and scalar multiplication simply by taking linear combination of these E1, E2, En, and therefore these are called basic column vectors in the n-dimensional space. So n-dimensional space Rn is identical with the space of n by 1 matrices, right? So Rn cross 1 is same as Rn, but we will think of elements of Rn as column vectors, and so therefore it says that all column vectors or all vectors in Rn are linear combination of these basic column vectors E1, E2, En. If we have a arbitrary matrix of size m by n with real entries aj k, then aj is called the jth row vector. So the jth row vector has entries as aj1, aj2, ajn, and similarly we have we can display the matrix in terms of the row vectors. Yeah, it's a m by n matrix. So there are m rows, there are m row vectors a1, a2, am. So we can write the matrix by displaying the row vectors. Similarly, I can write the kth column vector is A1k, AMK transpose. So see how I'm writing the column vector as transpose of a row vector. Okay, so this is the kth column vector of A, and there are if my matrix is m by n, so there are n column vectors, and we can display the matrix in terms of column vectors. First column vector as C1, second column vector as C2, and nth column vector as Cn. So you will see later on that we can use both these notations to display a matrix either row wise or column wise. Yeah. Now we go to the next operation among matrices. This is the matrix multiplication. Right now it is not clear how we are coming up with this strange definition of matrix multiplication. But later on, when we study linear transformations, you will see that this definition is kind of forced on us. Okay. So before we discuss product of matrices, general matrices, we define product of a row vector. Row vector is having n components, and a column vector which has n components. So take a row vector and column vector with same number of components. We will first multiply them. So display the entries of the row vector as a1 up to an, and the column vector as b1 up to bn transpose. Then the product of this row vector and the column vector is simply the dot product of these two vectors, a1 b1 plus an bn. Okay, yeah. So this is how we take dot product of two vectors in Rn, and we think of this row vector and the column vector as elements of Rn, n-dimensional space, and take the dot product. But the dot product is we are writing by putting the row vector first and the column vector next. So that is the product of a row vector and a column vector. The definition demands that the number of components of A and the number of components of B are equal. So both the row vector and the column vector have same number of components, then we will write A times B. Okay. Suppose I have the matrix A, m by n matrix, then there are m rows. I can display the matrix by displaying the row vectors a1, a2, am. Yeah? And so recalling that B is a column vector, we will define A times B. Okay, so I'm taking the matrix A, which is m by n, and I'm multiplying on the right by a column vector with n components. So number of columns of A is same as number of components of B. Okay, then we can write A times B. So display the row vectors A1, A2, Am. There are m row vectors, and times B. So all these row vectors have n components, and the vector B also has n components. So we can take the product of A1B, A2B, AMB, and A times B is a column vector with m components, and the components are simply A1B, which is the dot product of A1 and B, and AMB, which is dot product of AM and B. So this is how we are going to write the product of a matrix with a column vector. And of course, we are not taking an arbitrary column vector. The condition is that the number of components of B is same as number of columns of A, and the answer is a column vector of the same size. So the matrix A is sort of acting like a function. The input is the column vector B, and the output is a column vector in the same space. So B changing over m-dimensional space, right? M-dimensional space consists of all the column vectors of size m, of length m or m components. A times B is also varying over all the vectors in the same space. So input is B, the output is in the m-dimensional space. Okay, B. So the matrix A is acting like a function. So B had n components, so n-dimensional space into an m-dimensional space. So with using the matrix A, we have a function from n-dimensional space to m-dimensional space. The matrix is m by n, but as a function, it is acting on n-dimensional space, and the output are vectors in m-dimensional space. So in the language of calculus, this is a vector field. Yeah? Output are vectors. Yeah? Input are also vectors. So the matrix A defines a function on the space of on the space of n-dimensional vectors, and the output are m-dimensional vectors. Okay. We will see when we study linear transformation that these are the typical examples of linear transformations from n-dimensional space to m-dimensional space. That is, take a matrix, then A times B is equal to B, and many times we will see that a matrix is understood by its action. Yeah? Any object in mathematics is well understood when we know what is its action. So the matrix A, we started like a static entry, but now A becomes a dynamic entry. Okay? It's a dynamic object. So it takes vectors, input as vectors, and output are also vectors. So it is a vector field. Okay. If B is a n by p matrix and A is m by n matrix, we will display the column vectors as b1, b2, bp. Yeah, these are the column vectors where they have n components, and A is a m by n matrix and B is a n by p matrix. Then we can define AB1, ABP by using this rule that I just displayed. A times B is A1B, A2B, AMB. Then we know what these vectors are. AB1, ABP, they are all sitting inside m-dimensional space. Yeah? And so we will define A times B as a matrix of size m by p, where the column vectors are AB1, AB2, ABP. Okay, so this is how matrix multiplication is defined. That the matrix A, which is on the left, is acting on the column vectors of B and giving us the column vectors of A times B. Okay, so we let A act on each and every column vector B1, B2, BP, and the resulting column vectors are AB1, ABP, and these column vectors, they constitute a m by p matrix. So there is a restriction here. A is a m by n matrix, and if we are multiplying on the right by a matrix B, it has to be n by p matrix. So number of columns of A is number of rows of B. Then only we can multiply A with B in this fashion. Okay, so therefore, if I display the row vectors of A and the column vectors of B as A1, A2, AM, and B1, B2, BP, then the result is this m by p matrix, where the first row consists of dot product of A1 and B1, dot product of A1 and BP. Then the last row consists of AM B1, AM BP, and it's a m by p matrix. Okay. Yeah. So that's how we are multiplying. So think of A as A consisting of row vectors. If we are multiplying A with B, display the row vectors of A, display the column vectors of B, and to write down the jth, the entry in the jth row and kth column, we will simply take the jth row of A and kth column of B and take the dot product and display the kth entry of the product. Yeah. So here are some properties. If I take a matrix A, which is m by n, a matrix B, which is n by p, then AB is a m by p matrix, and for j equal to 1 up to m and k equal to 1 up to p, AB, if I display the general entry of AB, which is Cjk is the real number which is obtained by taking the dot product of jth row of A and kth column vector of B. And therefore it is sum of sum varying from L equal to 1 up to n, AJL times BLK. So, just keep this notation in mind. If you know what it is, then it is clear. Okay, yeah. So this is the, in terms of notation, what I just said. Display the jth row, AJ1, AJL, AJN of A. Display the kth column. Take the dot product, that is AJ1, B1K plus AJ2, B2K, etc., and add them. So then you get the jkth entry, which is we write as Cjk. Okay. So product A, B, AB is defined only when number of columns of A is equal to number of rows of B. So we can't multiply arbitrary matrices. This restriction is there on number of columns of A and number of rows of B. They must be equal. And then A is m by n and B is n by p. Then A times B is a m by p matrix. Okay. Using this definition, you can check that if I have A m by n, and I take a n by n identity matrix, multiply on the right, I get A. Similarly, if I take m by m identity matrix I and multiply on the right by A, I get A. A times 0 matrix, whenever the product is defined, is going to be 0 matrix. All entries will become 0. 0 times A will also be 0 whenever these products are defined. Okay. So identity matrix is kind of acting as the identity of multiplication, and but when you multiply 0 matrix with any matrix, you get 0, just like when you multiply 0 with a real number, you get 0. Okay. But we want to be careful about multiplying by matrices, because when you can multiply A with B in either way, that is both AB and BA are defined, the product AB and product BA may not be equal. Okay. I'll skip this part. For you to practice, you should know how to multiply matrices. I explained how to do that. So if A has these 2 row vectors and B has 4 column vectors, you see that there are 3 components in every row vector, and there are 3 components in every column vector. So take the first row vector and multiply by the first column vector to get the 1, 1 entry of A times B, and that happens to be 2. And likewise, you can get all the entries of A times B, and the size of A times B is 2 by 4, while A is 2 by 3 matrix and B is 3 by 4 matrix. When you multiply them, 3 disappears and we are left with a 2 by 4 matrix. Okay. Both the products are defined if and only if A is a m by n matrix and B is a n by m matrix. Then only we can multiply A with B in either way. But in general, the product of A and B and A, they are not equal. Like the product of dot product of 2 vectors with same components are equal. It doesn't matter how you multiply them. And similarly, product of real numbers, it doesn't matter how you multiply them. The ordering doesn't matter. But with this definition of multiplication of matrices, it does matter how you write A and B. Okay, so AB is not equal to BA. For example, just take this very simple matrix, 2 by 2 matrix with a lonely entry 1 and other entries are 0, and B is the this matrix 0, 1, 0, 0. You just multiply and check that AB is this matrix while BA is the 0 matrix. AB is not the 0 matrix and BA is the 0 matrix, so AB is not equal to BA, right? So AB is not equal to B, right? You can just check that AB equal to B, but it is not equal to 0. Okay. So if A and B were real numbers and B was, you see that B is a non-zero matrix. So A and B are non-zero matrices. Their product is B, but we cannot cancel B from this equation AB equal to B, because if you could cancel, then A will become the 0 matrix, but it is not the case. Yeah. And since A is not the identity matrix, we see that the so-called cancellation law doesn't hold. So if I write AB equal to B, you don't cancel B. Okay. We will see that sometime you can cancel B. Yeah? But in this case, if you cancel B, you will get a contradiction that A is identity matrix, which is not the case. Okay. So be careful. Cancellation law doesn't hold in the matrix multiplication operation.